Okay. We are recording this call. So good morning, everyone. Welcome to our latest Lockstep Technology Group Tech Talk. Is our first one for 2024, and one that I've been interested in doing for the last couple of years on basic network troubleshooting. I think it will be a good session. We are recording it, so if you want to pass it on to any of your colleagues, the link, I will send the link to you after the, well, if you're on my email list, I will send you the link to the recording. If you're not on my email list, but would like to, be apprised of any kind of tech talks or classes we've got, or copies of these sessions, feel free to shoot me an email and I'll be glad to add you to my email list. But I promise I won't spam you. I won't be sending you stuff every day. Okay. So let's get started here. I'm going to leave this as is. Actually, I think I'm going to go into presentation mode, and everyone should see that fine. If you do have a question, folks, I would ask that maybe you'd shout out the question as opposed to putting it in the chat window, because I'm running this solo. So it would be easier for me to respond to your questions if you just give them to me orally. So let's get going. Before we get going, though, I just want to let you know about our next Tech Talk. And this one is sort of an update of the one that I gave back 3 years ago when I first came to what was back then Transformix, and it's now Lockstep Technology Group. But it's sort of an update on IPv6. Where is it on the planet? What's the state of it? And the title of it is IPv6 Mostly, a Step in the Stated Direction. And yeah, see, one of you folks put a note in there, shudder. One thing, if you don't know me, I'm a big IPv6 fan. I think it's long-term, the way we're going to go. I just wish it would move faster, but suffice it to say that it actually is moving faster in terms of adoption than we think here in the U.S. We've got sort of a distorted view of the deployment of IPv6 worldwide, but it's growing very fast, and particularly in certain sectors and certain geography. So I'm going to have one of my former colleagues when I was at Cisco, a gentleman by the name of Tim Martin, to come on and give us an update. He's entitled this IPv6 Mostly, a Step in the Stated Direction. Tim is an excellent presenter. He's, if any of you have ever attended Cisco Live, he is one of those. He's in the Hall of Fame for Cisco Live presentation. He is one of the leading IPv6 consultants and evangelists in the U.S. and, dare I say, in the world. Very knowledgeable, great presenter. I think you'll get a lot out of this. And why would you care? Most of my customers at this time are not running IPv6. Well, I would say you may not be running IPv6 because you've done things proactively to run it, but it is, in fact, running on your network. I would hasten to say that 95% of you have IPv6 running on your network today. And if you don't want it to run, or it worries you a bit, maybe a session like this might be helpful, because it's good to learn about what's actually running in your network, I would say. So stay tuned for that Thursday, March 14th at 9 a.m. Central Time. Should be a great session. Okay, so let's move on to our topic at hand, basic network troubleshooting. So I made some assumptions and some caveats regarding this session. So this session is focused on basic network troubleshooting, not advanced troubleshooting. And it looks like a lot of folks from that are on this call are from help desk areas. So that's great. You folks are a lot of the audience that this is targeted for. So it's good to see that. So I do suggest that you are familiar to some extent with the OSI reference model. Hopefully that doesn't scare you away, but we'll talk about it for just a second. We're going to spend a lot of time on it. But having some idea of what the OSI reference model is helpful. I make the assumption that you are not a seasoned network engineer, but you are familiar with layer 2 and layer 3 networking and addresses. So MAC addresses and IP addresses, those things should sound familiar. And if you see one in the wild, you could probably identify that and say, oh, that's an IP address or that's a MAC address. We're going to use Cisco devices for this session, but these learnings should apply to other vendors. So don't think this is a Cisco. If you don't run Cisco gear, you're not going to get anything out of this. That's not true. Okay? Because networking is networking. So this is the OSI reference model, the 7 layers. It's on the right-hand side of the screen. Don't worry, we're not going to get super deep here. But having some understanding of these networking layers is helpful. Failure to have any idea of or understanding whatsoever of these layers is going to lengthen your mean time to diagnosis. So that's why you want to know this. Got a problem, you're on the gun, you want to solve it quickly. Having skills that understand the different networking layers will help you solve that problem quicker. It helps you make educated guesses early, where to look for the problem and where to not look for the problem. That's why you want to know this stuff. Okay, it's not just about working hard when troubleshooting, it's working smart and quick. Now, there are 7 layers to the OSI reference model, but the ones that, as a network engineer, that you're going to be most interested in are the bottom 4, 1, 2, 3, and 4. At the very bottom, we have what's called the physical layer, and that deals with the bits that are put on the wire, cables, whether it's copper or fiber cables or radio frequency signals. For example, if my Ethernet cable is unplugged or it has broken pins or my wireless RF signal is too weak, those are examples of layer 1 problems. So if I've got broken pins on my Ethernet cable, there's no need to look at the layer 2, 3, 4, 5, etc. areas to solve this problem. I got a layer 1 problem. Now, if we go up to the second layer, the data link layer, this is the Ethernet switching layer. This is where forwarding of frames or packets is based on those MAC addresses. They're 48 bits long, and I have an example of one right there. Those should look somewhat familiar. MAC addresses. And quite often, what I find when I am troubleshooting with customers, they do not pay attention to the MAC addresses nearly as much as they should. Always, particularly if when you're troubleshooting a network issue and you have a good idea who the culprit is, let's say in terms of the IP address, make sure you understand who their MAC address is too. So that is important. We go up to layer 3, we have the network layer. This is the IP routing layer. This is where we forward frames or packets based on their IP address. That's that 32-bit address, like the example I give you, 10.5.20.1. That should look familiar to you. And then we move up to what's called the transport layer, layer 4. This is the layer where we're using protocols to get more specific as to specifically what kind of application are we trying to communicate with. And the 2 primary protocols that we use to do that are TCP and UDP. We're not going to go in details about that, but just remember that those are the 2 primary layer 4 protocols. And also at this layer is where we denote what are the source port numbers and the destination port numbers. For example, if you've got an application that's using destination port 80 or 443, I would bet most of you are kind of familiar with that and say, oh, that's probably HTTP or that's an SSL connection. Those port numbers are probably familiar to you. Those are well-known ports, the destination ports. The source port is the client talking to that service, and the client can pretty much pick out any port number they want. In this particular case, it's port number 56463. Probably you look at that and say, I don't know anything about that one. Well, that's a port number that's called an ephemeral port number. It's chosen by that source for that particular point in time and may never be used again by that client for a very long time. But the important ones are, where are you going? What port number are you going to? port 80, port 443, port 53, etc., etc. Those are the things to look for. Now, it's often helpful to know what type of device might be the culprit. Let's say you have some vague feel that I think I know who's causing this problem. I'm not sure, but I think I do. Well, a good tool to help you out here is a Mac OUI tool. OUI stands for Organization Unique Identifier. You can Google that. Google Mac OUI tool, and you will come up with various tools. One of the best is the one by a company called Wireshark. And once you get to that page, in that white space there, that's kind of small, you will place the MAC address in question. And the results you get back will typically be the vendor ID of that MAC address. Now, the value of that is, now I know that, this is a Cisco device, or this is a Dell device. So you learn the type of device that's on your network, and that is the possible culprit. And then you might ask yourself, well, is that the type of device? Why is that type of device on my subnet? That's an IoT device. I shouldn't have that type of device on this subnet. Or coming from that IP address, the MAC address should be maybe something that's maybe a Dell machine. Why is it another machine? So having this additional information can be very, very useful. Now, one caution is that some of the operating systems now offering randomized MAC addresses. Well, it's good for obfuscation, but it hurts a little bit when you're trying to do some troubleshooting. Now, one of the best, very best tools for troubleshooting and for learning networking is a tool called Wireshark. Wireshark is software you can download to your laptop, whether it's Windows or an Apple device. It's a great tool for troubleshooting, great tool for learning networking. It's free, and you can use it to do the heavy lifting. Wireshark's got a lot of bells and whistles to it, but you don't have to go off to class to learn about it. There's tons of free VODs on YouTube to learn how to use it. It's free, and it's and again, I can't stress this enough. One of the great things about it, it's a great learning tool. So please pull down Wireshark and get with it. Okay, and it's free. Okay, there's an example of a Wireshark screen there on the right-hand side, and every row represents a packet, a data packet that was captured by Wireshark. And so now you can look at these packets and see, okay, what was that device sending and receiving? Okay, we're going to dig into that a little bit. Now, how would you make use of Wireshark? Well, a very typical and a very simple use case would be, let's say you've got this big orange Ethernet switch there, and the device whose traffic I want to capture, maybe I suspect this device as being a problem. It's connected to port gig 1/0/4. So we know that. We take our laptop and we've installed Wireshark on it, and we plug our laptop into another Ethernet port on that switch, in this case, gig 1/0/10, and we enter the commands on the switch to tell the switch, hey, any traffic that's coming to port 1/0/4 or egressing from that port, I want you to send a copy of it over to gig 1/0/10. And all that traffic goes into that laptop into Wireshark. Above the switch, you will see the commands you would use if you are running a Cisco switch. Now, the nice thing is that all vendors have this capability. It's not just Cisco. And many vendors use GUI dashboards for management of their network. So they make it even easier for you to enable this kind of a mirroring of traffic. And notice the port that the culprit device or the suspect device is connected to is called the mirrored port. So you often hear this referred to as port mirroring. Also, it's called span. I think it's Switch port analyzer is what that stands for. So this is basically how you do it. There are a lot of variations on how you do it, where perhaps the source device is on one Ethernet switch and the laptop is sitting on another one in another part of your network. You could do something like that. Now, you've got this nice Wireshark trace. What can it tell me? Well, let's look at a packet. Do you see row 9 highlighted there? That's an individual packet. Well, it's got some layer 1 information, and the primary thing it's got in there is the length of the packet on the wire. It's 1,514 bytes. Just so you know, each byte is 8 bits. So if I take 1,514 bytes times 8, that's a total of 1,112 bits long. Now, knowing this might help me solve a problem. I think I have an MTU problem. MTU stands for maximum transmission unit. The idea of a maximum transmission unit basically says you want to go from point A to point B, and one could be in Baton Rouge, one could be in California, the source and destination. The MTU defines the largest packet that can flow from one end to the other before it has to get chopped up. So MTU is very important and is a cause for a lot of networking problems, especially when the packet that's in transit that's too big, that is going to exceed the maximum transmission unit somewhere along the path. If it has the do not fragment bit set, that can be a problem. So that's some layer 1 information. How about some layer 2 information? Well, I look at the layer 2 information. The main things I get here are the source MAC address and the destination MAC address. And notice that Wireshark is smart enough to know that, hey, this MAC address, the first 24 bits tell me this is the destination. The first 24 bits tell me this is a Cisco device. And for the source, the first 24 bits tell me this is an Apple device. This is good information, So 2 things about this. Let Wireshark do the work. It knows the MAC OUI to vendor mappings. And then you have to ask yourself this question. Are these the MAC addresses or devices that I expect? This is a very, very common problem where you're focused on the source IP address and the destination IP address, and you don't even think to look at the MAC address underneath. You might find that, well, that MAC address is incorrect. That shouldn't be that MAC address. I've had multiple occasions where some device on the path has basically taken over the IP address, and it's using, so its MAC address, it's actually taking all the traffic through it. And if you don't pay attention in the Wireshark trace appropriately, you won't see that that's not the right MAC address. It should be something else. So pay attention to that. Now we also have some layer 3 or IP routing layer information. There's tons of stuff in that Wireshark gives us there. At the very top, the top oval there is all about what are called quality of service settings. What are they? Did some application set the quality of service settings so that this traffic should get priority behavior across the network? Or does it not? In this case, that none of the quality of service settings are set, so it should just get best effort behavior from the network. The second oval down below is the do not fragment bit. Okay, in this case, the do not fragment bit is set. So that means that if this packet is too big, the MTU is too big to egress out a particular port on a downstream switch or router, guess what? That packet is going to be dropped. And we're sitting here wondering, why are my packets getting over to the destination? So check this out very closely. You have the time to live that tells you how many routers this packet is going to. It's decremented at each router. In this case, it's set to 64. As soon as this packet goes to the next router, it will decrement it down to 63 and on and on. And then we also learn about, well, what's the transport layer above us that we're running here? We're running TCP. That 6 right there tells us this is a TCP application. And then down at the very bottom, we have the source and destination IP addresses. We can't forget those. That's important. So lots of useful information for layer 3 in the Wireshark trace. And then we go one more layer higher, the transport layer. And we see those source and destination ports that I was talking about. The source port, the client, is used port 57325. That's one of those ephemeral ports. It just kind of goes away. And then we have the destination port. That's 443. That's typically SSL. That should be a pretty darn common destination port. They're using SSL. And inside of that red or pink rectangle is a lot of information about the state of this TCP communication. So this application is using TCP, and it's doing so because it needs the reliability of TCP. It needs to know that all of the packets are getting across and no packets are lost. Now, to make that happen, TCP have to keep track of the state. You know, how many bytes have you sent? What's the next byte you expect to send? The next byte you expect to receive, et cetera, so that the source and destination can always stay in sync and nothing is lost. This is very important. We're not going to dive into this pink area. Suffice to say, if you ever need to get that information, it's there. Let me see. Does the maximum MTU define the size of the transmitted data or the transmitted data and size of the headers? It's the whole thing, the whole shooting match, the whole pack. Hope that answered that. Okay. Now, when we begin our troubleshooting, you got to do one thing: listen and ask questions before you strike out in any direction. The people who are reporting the problem, ask them some serious questions. Exactly what is the problem? And try to get them to be as precise as possible to outline the problem. For example, no one in the Detroit office can get to Microsoft 365. That's pretty good. Okay. Another question is, when did the problem start? For example, did any changes occur shortly before the problem started? For example, we switched to a new WAN provider. Does the problem occur all the time or only at certain times? This is one that I see happen a lot. For example, the problem only occurs during the heat of the day when all our users are there, and the problem goes away during lunchtime. Then it raises its head again right after lunch, and then goes away when everyone goes home. Sometimes that's very good, but also sometimes that typically means that this is related to the load on the network. Okay. Is the problem repeatable on demand? That's always helpful. Can I cause this to happen over and over again? Because that helps you really drill into solving it. Are all the apps affected or certain ones? Here's one where the call into help desk is internet's down and I can't get to anything. Okay, that may be the case. Let's drill down into that. Can you get to certain areas of the internet and not others? Can you ping certain places out on the internet? Things like that. Drill down in there, okay? The two things to remember: confirm all the answers to the extent possible. I've had many times where I've had to go back and ask the question 2 or 3 different times, and also get my customer to talk to several people within the organization, particularly ones who actually, trust but verify, as Adrian says. I've had to go back and ask the customer, let's talk to some of the people who are calling in the problem, and let's try to drill down. You know, what were they specifically trying to do? So confirm all answers. And the intent is to limit the troubleshooting zone. For example, if we learn the Detroit office can get to the internet, but not Microsoft 365, that's going to help us focus our efforts and reduce the mean time to diagnosis. In this particular case, that tells me whether internet's up, it's just that access to perhaps certain applications may be the problem, okay? So where the problem is and where the problem isn't. General rule number one. If the problem is not seen at a specific OSI layer, then it is unlikely that the problem exists at a lower layer in the OSI model. For example, if I can successfully ping a device, it's probably not a layer 1 or a layer 2 problem, since a ping is a test of the layer 3 connectivity between two devices. That's that IP routing layer. So if that's working, well, I doubt layer 1, layer 2 are places worth looking at. To paraphrase Horace Greeley, go north, young engineer. Now, general rule number 2, there are no absolutes. For example, if I can ping a device, but I get some quantity of failures in those ping attempts, for example, I send out 500 pings and I only get 450, that's a lot of drops. Then I may, in fact, have an intermittent layer 1 or layer 2 problem. So just be careful there. Now, I always like to do a packet walk to help folks understand how packets flow through the network from end to end and where those addresses or headers change along the path, or do they in fact change? Because this will help you in your troubleshooting, and it will help you understand if you're expecting to see certain addresses at certain places along the journey and you're incorrect in your understanding, well, then you're chasing a red herring. So let's do a little packet walk here. To start this off, you have to remember something. At the OSI layer 2 layer, that's the Ethernet layer, the switching layer, the data link layer, whatever you want to call it. Among other things in those headers, you have the source MAC address and the destination MAC address. Those are those 48-bit addresses that I'm sure you all see every day. Now, these MAC addresses are transient in the header. They only exist for the local link or the local LAN or the local subnet, okay? For example, you see the PC on the left-hand side. It's going to create a packet, and inside the packet, well, you can see the layer 2 header with the source MAC and the destination MAC address. And we'll put that in that packet, and the packet flows across that local LAN, that local subnet. There may be a handful of Ethernet switches on that subnet, but that packet flows intact across that subnet, and it hits the first layer 3 router or switch, the orange box. That orange box, before it decides that it has to send that packet on its way out the port on the right-hand side. Before it does that, it's going to change those MAC addresses in the headers because the MAC addresses are transient. And this happens all along the path, such that when you get to the server at the far end and you look in the layer 2 header of the packet as it arrives at that server on the right-hand side, those MAC addresses won't look anything like the MAC addresses, source and MAC addresses that were sent at the very beginning by the initial PC on the left. Now, let's juxtapose that to the OSI layer 3 header, which includes, among other things, the source IP address and the destination IP address. Well, the nice thing about these is that these IP addresses are kind of like diamonds. They are forever. They stay in the header from end to end, all the way from the source PC to the destination server. Keep those two facts in mind, and let's do this little packet walk. Okay, we've got 6 points along the path that we're going to look at the header, and you need to tell me, or we're going to figure this out, what those headers are populated with in terms of the layer 2 MAC header, source and destination MAC address, and source and destination layer 3 IP address. So if you look at each of the devices, we've identified those addresses, both the MAC address and the IP address. So let's start off. So that PC wants to talk to the server on the far right with address 3.3.3.5. His address is 1.1.1.10. His MAC address is A, he's the source, and the destination MAC address is B. Let's look over at that server on the far right. His MAC address is F. Something doesn't compute. Well, no. because the destination MAC addresses are transient. The destination MAC address that the PC should send out should be the one for the default gateway, that layer 3 router, that first one on the left. Notice that layer 3 router's MAC address on the port on the left-hand side is MAC address B. Everybody get that? Okay. Now it goes to that first layer 2 switch, that blue one, and it's going to send it on its way. And notice it changes nothing. Nothing changes in the MAC address headers or the MAC headers or the IP headers. And then we go to the layer 3 router. This is the first layer 3 hop. Notice the IP addresses don't change, but guess what? It replaces the source MAC and the destination MAC. Everybody see that? And then we go down to the next layer 3 switch, and it replaces nothing. It's kind of, you think of it as being transparent in terms of the layer 2 and layer 3 headers. And then the packet goes out to the last router, and his source MAC is E and his destination is F, which is finally the MAC address of the server. And the IP addresses remain the same. Then we hit the last layer 2 switch and nothing changes. So what changed regularly? The layer 2 MAC addresses. What never changed? The layer 3 IP addresses. This is extremely important. If you did a Wireshark trace on the layer 2 switch at the far right at the port connecting the server to the layer 2 switch, and you were expecting to see MAC address A as the source, then you're sadly mistaken. They're transient. But if you're expecting to see source IP address of 1.1.1.10, then yes, you are correct. Does that make sense? Okay. So this is a good little tool here I like to run through. Now, I got a user complaining about connectivity problems. Early on, you should get their network configuration information. Get them to do an IP config /all, and I'm assuming this is a Windows environment. You have the if config in say an Apple environment. And get that information and ask yourself a few questions. Should this user have an IP address in this range? This is a problem I've run into multiple times. This user should be in subnet X, which should be 192.168.1. something, and nope, I'm seeing a totally different address space. It's in a 10 address space or something like that. Is the default gateway correct? That's a good one to check. Is the subnet mask correct? I've seen that problem happen multiple times, especially when you're doing manual configuration of the IP addresses. Yeah, or as Adrian says, if they have IPA address. Okay, true. Do they have a DNS server? Should they be configured for DHCP? If so, is this the correct DHCP server address? Do they have a DNS server defined? If so, does it look correct? And make note of that physical MAC address. You might need it later. I can't stress that enough. So interrogate all of this. You might find that there's something that's incorrect here that can save you a lot of time. Okay. Now, is it a routing problem or a DNS problem? So you did have them do an IP config. And in that IP config, you do see that they've identified the DNS servers. So the user says, I cannot get to www.acme.com from my Chrome browser. Well, is it possible they can get to that device using an IP address? You may not be aware that you can, but you can sit in your browser and instead of typing www, the DNS name, put in the IP address of the device. If you're able to resolve it, go into NSLookup or something, and you happen to know the IP address. Can you get to that device via the IP address? If yes, then you have a DNS problem. Okay. Does your client have a DNS server defined? In this case, we see down there, yes. Okay. If yes, can you ping this DNS server? If you can't, and that could be a problem, but sometimes, people block things like pings to servers like DNS servers. If you can, then let's make sure it's actually performing as a DNS server. So you can do the NSLookup tool. Lower left-hand corner is an example of using the NSLookup tool in a command prompt. and and making sure that, oh yeah, this thing is acting like a DNS server. Okay, but it's a good way to sort of decide, do I really have a routing problem? Is the internet down, or is it really just DNS that's down? Good. If anybody's got a question, please shout it out. Again, I don't have good visibility into the, let me see if I can check the chat window real quick. Okay. Gotcha. Okay. Now, if you're in a Cisco environment, particularly like a Cisco Catalyst environment, know these commands and understand their output. Now, every vendor is going to have a way to get this type of information. Okay, every enterprise vendor, whether it's HP Aruba or Juniper or Extreme, Meraki, all of those vendors have ways to get this information. But for purposes of this talk, we're focusing on the Cisco way to do it. So these are all good commands. Okay. Whenever possible, enter these commands with optional parameters, because that will limit your output and speed your troubleshooting. You know, don't do a show IP route and hit enter when you've got 5,000 routes. Do a show IP route and put in the specific route you're interested in to limit your output so we can move things along. Also, logs are a very, very valuable source of information, but they're not so valuable if the clock on the device in question, like the switch or router, is incorrect. Make sure your clock is set correctly, okay? A very, very good command, and probably the very first command that Cisco TAC will ask you to get, is to do a show version command. This is a great command. It tells you, well, what the heck kind of device is this? What kind of interfaces does it have? How much RAM does it have? What kind of licensing does it have? This by itself is very, very crucial information, because if you're troubleshooting a problem that you think it's a network infrastructure device and you haven't even found out, well, what the heck kind of device it is, that can be problematic. Do this very, very early on. Show version or a similar command from another vendor. And make sure your switch or router's clock is correct, and use NTP. Don't manually configure your clock. Use NTP for all your infrastructure devices, so that, let's say you're looking at a log from one device and a log from another device trying to solve the same problem. It would help if the incident or log event that we see in one log matches up with the time frame of the incident on the other log. Okay, use NTP. And that's just an example of how to do it in a Cisco environment. And look at your logs. The show logging command is a way to do it in the Cisco world. Don't wait 2 days later to start looking at your logs. Look at your logs immediately. There's often a lot of great information. Look at it as soon as you get a handle on the problem, to some extent, to know that this switch or router may be part of the problem. And as you can see down at the bottom of the screen, you can use optional parameters to focus that search. For example, I suspect that I've got an OSPF problem, so I don't want to see the whole log. I just want to see the log messages that are related to OSPF. And by doing that command with the I space OSPF, like in I is include only OSPF messages, that's great. Also, Adrian makes a very good point. Look at as soon as you can look at the logs, because the logs fill up. And so it's quite possible that your logs you're just turning over, every 3 or 4 minutes. So yeah, very good point there, Adrian. Know your network topology. Don't trust manual drawings. Do things, if you're in Cisco world, do a show CDP neighbor. Great tool for knowing the devices that are directly connected to you at layer 2, okay? So here we did a show CDP neighbor. We're seeing the left-hand column identifies a device ID. Then the next column, local interface, says, well, which port on this switch or router is it connected to? The capability and platform help you identify what kind of device it is. And then the last column on the right identifies the port on that other device that you're connected to. Now, if you're in a non-Cisco environment, use the show LLDP neighbor command or something similar to that. But essentially, in a non-Cisco environment, you would use LLDP to functionally do the same thing as CDP. Now, you can do the show CDP neighbor detail, or DET for short, to get more detail other than one line per device. In this case, I'm learning a lot more about a particular device, its IP address, what kind of device it is, etc. So sometimes you want to do that. And one of the most important things you want to do, because we're talking routers and switches that run networks, right? Routers and switches, or say firewalls, but any kind of networking device, it's all about packets flowing through interfaces, going in interfaces and going out interfaces. So check your interfaces, okay? Make sure that the interfaces in question are all, in the Cisco case, when you do a show interface, make sure that it is up and up, as I depict in these red rectangles. If you don't have up and up, Houston, we got a problem. And as you can see, there's tons of information for that particular port. Take a close look at this, okay? Lots of juicy information for you to find out if something's wrong. Are we seeing errors? Things like that. This interface, in this particular case, what I'm showing here, this interface is capable of running at 10 gig. Note its hardware MAC address there. You see that? It says it's a 10 gig capable port. But in fact, it's only running at 1 gig, okay? Is this what you expected? I thought I had a 10 gig SFP and only got 1 gig. Maybe that will explain why I'm overrunning this port. It should always be full duplex. If you ever see a port at half duplex, you have got a problem, particularly if you're running any kind of a voice or video over that port. Look at the MTU. In this case, it's 1500. Is that large enough? One of the things I will tell you, that in data center network infrastructures like data center switches, the general rule is you want to have your MTUs much bigger than this. You really want MTUs that might be over 9,000 bytes, because the traffic inside of a data center, particularly going east and west, is a lot of data, particularly to and from storage devices. And the larger you can make those MTUs, a larger amount of data can be sent in an individual packet, which means the network and the applications run that much more efficiently. So remember that, particularly inside of a data center. Also, take a look at the amount of traffic that's ingressing into the port and the amount of traffic that's egressing out of the port. Does that look right? You know, if you're a typical customer environment, the port that's facing the internet, or if in the direction of the internet, that's typically a port where the amount of data coming into the port is typically much higher than the amount of data going out of the port, because we tend to be, you know, importers of data from the internet. Most customers are. There are variations on it, but check and make sure that looks good to you, okay? Are we seeing any errors or drops or buffer failures? Presence of counters could mean that you got a layer 1 issue, or you have buffer shortages, or you have bandwidth constraints, okay? And always when you're looking at this show interface command, do it during the peak traffic time of the day. You know, when everybody's banging away at it. Don't do it at night unless there's some specific reason. But if you suspect that you are just overrunning the network, do this command multiple times, say during the peak hours of the day. So I'm suspecting that I've got a device with this particular MAC address causing a problem. Where is it? Because it could be that I've got a big layer 2 network with about 30 layer 2 switches all connected together. That's a lot of ports. That could be literally thousands of ports. You know, where's Waldo? So a good tool to use is use the show MAC address table command. And you can suffix it with optional parameters that help you trim it down. But in this case, I've done a show MAC address table, and you will see on the left-hand side of the screen, the oval near the bottom, I've identified that particular MAC address. Oh yes, we see it. It is in VLAN 100, and it's that switch learned about it on 10 gigabit Ethernet 1/13. Aha, the game is afoot. Now I know where to go look for this MAC address. So also, now that I have the MAC address, I can learn which type of NIC this is, network interface card, and it's in fact an Intel device. Dynamic in that output means that it was learned by the switch, okay? That switch saw traffic from this MAC address, so it put it in its MAC address table. And it saw it again on interface T1/13. So the question is the device really connected to that port, T1/13? Well, in this particular case, it is not. T1/13 is a trunk port that trunks to another downstream switch. Aha. So then I need to go to that switch and start my show MAC address table command again and follow the breadcrumbs, okay? This is again where the show CDP neighbor is a great tool. On the lower right-hand side, I did a show CDP neighbor from the original switch I did the show MAC address table from. And sure enough, it says that hanging off of port 10/1/13 is a 2960X. And it is a trunk. And I can then go to that switch and trace down the breadcrumbs to ultimately find where that device is. And maybe I just have to shut down that port or tell the user, you've got to remediate that device. It's got an issue. Now, I've got a MAC address. I'd like to map it to an IP address because that can be really helpful. So the first layer 3 switch that a device is connected to, sort of its default gateway, if that device has been sending traffic and it's got an IP address, we'll see that IP address in the ARP table. So I can do a show IP ARP. And here I have I know the IP address 10.191.123. And when I do that show IP ARP command, I map the IP address to the MAC address. Ah, great information. Now, armed with that, I can then do a show MAC address table with that address, that MAC address, and I learn that is it on 10 gigabit Ethernet 1/13. Now I can start hunting down where that MAC address is. So the network is slow. Could it be a spanning tree problem? Here is a spanning tree network with 5 switches that is not built very well. What happened in this particular case, the end user, you just unwrapped all 5 switches from the packaging, plugged them in, changed none of the spanning tree parameters. And if you know anything about spanning tree, all these switches are going to talk to each other and they will determine who the root switch is. And once we determine who the root switch is, we will build a loop-free topology from each downstream switch to the root. As you can see in this case, switch 5 is the root. Well, why is he the root? Well, the election of the root is based on, number one, which switch has the lowest bridge priority. And if you don't change the bridge priority by configuration settings, they all have the same bridge priority. It's 32.768. So all 5 of these switches have the same priority. Well, then how are we going to choose the root? Then we go down to the tiebreaker. That's the MAC address, the lowest MAC address. And lo and behold, switch 5 has, by chance, the lowest MAC address and becomes the root. And when that happens, good old spanning tree has to start blocking some ports or we're going to have a loop and our network will melt down. In this case, notice the 2 links that are blocking. That means that both switch 4 and switch 3 have non-optimal routes up to the core of the network. This is not good, okay? We need to fix this. No way to run a railroad or a network. So this might be a better way. Let's not let things default. Let's actually manually define a switch or a couple of switches as the that we want to be the routes. Okay. So here we've said switch 1, you're the one that's best connected. You're the closest to the core. You're well connected in multiple links. Let's set your bridge priority down. So in this case, we set it to 4096, and all the other switches will have a priority of 32768. So switch 1 automatically becomes the route. And now we're not blocking those links that connect those switches directly to the route. We have much more optimal routing. This is the way you want to do it. Don't leave your spanning tree to chance. Hope that makes sense. Here's an example of a spanning tree network. We have a loop here. We have 8 switches. We have 100 meg links between all the switches. And by default, their cost of each link is 19. And it has been determined that the route is a switch 6 there. Bottom row, second from the right. And you could go, if you can do the show spanning tree command, very, very good command, show spanning tree command, and you will determine, if you've got some sort of spanning tree problem, what is the topology of your network. In this case, if I look at switch 1 in the upper left-hand corner, it has a cost of 57 to get to the route. And if you notice, I've circled down near the bottom of that section a port that is the route port. That's the port that tells me the traffic should go that way to the route, and that's port FA02. That tells me that switch S1, when it wants to send traffic, it's going to send it down FA02 over to port switch S8, and then switch 7, and over to the route switch 6. Now, at some point, we have to block. There's got to be blocking going on because we have a loop and we're running spanning tree. And sure enough, if we look at switch 2, port FA01 is in alternate block state. This port is blocking. Now, it's logically blocking. The spanning tree packets are flowing, but no data packets. And if we were to break a link somewhere else, then that blocking port would no longer be blocking, it would start transmitting data. But this is always one of the first places. If I suspect a spanning tree problem, I always want to go in and do a show spanning tree. One of the things it tells me who the route is. If you look at the bottom below switch 6, in this case, for a Cisco switch, it actually tells you this bridge is the route. No questions asked. I know. And then I can understand the topology from then on. So very important spanning tree. Don't just let it run in the background with not knowing anything about it and not configuring it appropriately. Don't build large layer 2 switch networks. Limit your blast surface. I'm not a big fan of 50 switches in a layer 2 network by themselves. If you're connecting your switches with someone else's switches, some other vendors, make sure you understand the supported and the default spanning tree protocols that the 2 vendors are running, and make sure that you can configure them to a common subset. Don't disable spanning tree on a switch. Now, you can disable spanning tree on individual ports, particularly ports that are access ports. Now, an access port is a port that's just going to have an endpoint connected to it, not another forwarding device like another switch. In Cisco land, when you do this, you do the port fast command for that, and then you couple that with the BPDU guard command. The reason you may do this, if you notice, if you don't have port fast configured on a port and you plug a device into that port, do you notice that it might take 30 to 45 seconds before that LED turns green? That's the reason why. Sometimes with certain endpoints, that can cause problems, say with DHCP or Pixie Boot. So a good best practice for ports connected to end devices is to disable spanning tree on that port by using port fast and BPDU guard. Trunking issues. So trunking today should be using the 802.1q standard. So everybody runs that. So you want to, have VLANs in one switch, be able to connect to the same VLANs in another switch, do trunking. Make sure that you all agree on what the native VLAN is. Here we have a mismatch. Switch on the left says the native VLAN is 10. Switch on the right says 1. That's a problem. And that problem is reflected in the log. See below? It's complaining about the fact that we have inconsistency between the the native VLANs. So double check your trunking and make sure you all agree on all the VLANs that are supposed to flow across. And also additionally, I might have it here. Let's see. Yeah. So best practices with trunking. Make sure you both agree on the native VLAN. Make sure you both agree that each switch agrees that this is a trunking or an access port. You know, if one says access, one port says trunking, you got a problem. By default, all VLANs are going across the trunk, okay? And issues could arise when attempting to trunk between switches from different vendors. Understand the nomenclature and the default differences. Sometimes different naming conventions may mess you up. So here are some best practices. On the right is an actual configuration of a trunk port. Put a description on this port. It's a trunk port. It's connecting to something important. Let folks know. Configure it to be a trunk, not to talk the dynamic trunking protocol. I'd rather you not use that. Just type in switch port mode trunk. And don't let all VLANs flow across the trunk. Specifically articulate which VLANs will flow or not flow. Limit it. I've seen multiple times when allowing all the VLANs to flow can cause network-wide issues. Serious network. For example, I was working with a school district where they didn't do that, and the entire school, you know, probably 40-something switches would go down, disconnect from the network. So be explicit about what you're allowing across the trunk. My network is slow. Could it be that my broadcast domain is too big? Well, generally, the broadcast domain size equals your subnet size. What's an ideal broadcast domain size? There's no one right answer, but the key is to make sure that the broadcast traffic doesn't consume too much of the bandwidth. The bigger your broadcast domain, the more broadcast traffic. If you're running 100 meg links, excuse me, that could be a problem. Subnets of size maybe /20 or down to /24 are pretty common. Typically, you don't go bigger than a /20. /20s are often used for wireless devices, but they can typically handle that pretty good. But your mileage will vary. Now, you can build all smaller broadcast domains, smaller subnets. In other words, make sure everything's a /24. That's fine from a troubleshooting perspective, but it means you got to work more. It's more configuration, a little bit more network deployment, management, and complexity. So think about that. You want to draw a balance. How big is my broadcast domain? Well, that depends on your addressing. So in this case, I did a show run interface VLAN 100, and I see the interface VLAN 100 output, and its address is 10.190.0.1 with a mask, and this is the key. The mask is 255.255.240. That tells me this is a /20. So I can put 4,094 devices on this subnet, which may be okay, but just understand how big it is. Also note that right below that is the an IP helper address. That tells devices that need DHCP addresses where we're going to send you to get a DHCP server to give you an address. And make sure that the DHCP server has a scope big enough for those 4096 devices. The command below it tells you, the show MAC address table count VLAN 100 tells you how many devices are currently in the broadcast domain. In this case, it's only 177. I can't get to a particular IP address. Well, are you unable to get to the device via certain apps or protocols like HTTPS or FTP or etc.? Can you ping the device? Now, sometimes you won't be able to ping it, but because that could be that, you know, they've got the host firewall on and it's not allowing pings. Just be aware of that. You could perform a trace route to the device, but caution, sometimes this is blocked. Here's an example of doing a ping on a Cisco router that does the ping slightly differently, and by doing so gives you a lot more information. For example, I can mix in different repeat counts. Here, the line 4, the repeat count by default is just 5 pings. Well, that might not tell me enough. Maybe I want to do anywhere from 500 to 1,000 pings, and by doing that, I might find that I'm losing about 20% of my pings. That's an issue, okay? And that issue may not have been uncovered if I just did a repeat count of 5. The datagram size default of 100, maybe I need to adjust it. Maybe I should try, let me try a 2,000 byte MTU, see what happens there. Go down further, about 7 or 8 lines down. Let me source the ping from a different interface or IP address on the router. Now, the value in this is that it will uncover routing issues that you may not notice if you do a regular default ping, okay? And I'll come on to explain that. You could set the do not fragment bit to help you uncover MTU issues. And go on down, you run the ping, and maybe it's successful or maybe it's not. You can do that same command on one line by using the command I've shown below with all those parameters. The value in this is that if you do a ping with certain optional parameters, you are going to get a lot more information than if you just did a ping with no parameters. That's the key. Here's an example of doing a ping to a device, and I set the MTU to 1501, and I set the do not fragment bit. In other words, if you can't send it as one whole packet, don't fragment it, just drop it. And I do that, and womp womp, I don't get anything. Then I change it, and I drop it down to an MTU of 1500, and boom, everything works. I have just determined that my MTU is exactly 1500 bytes from end to end. That's good information to have. I could do a trace route. You know, that tells me the path to an end device, but what it does not tell me is the path from that device back to me. I could have asymmetric routing where I take one path to get to the destination and the destination takes another path to get back to me. Below are just some details about it, but this is a good tool, but just don't read too much information into it. It'll tell you if you're successful, it says, oh, that device is IP capable. I can get to it via IP routing, and it can respond. But don't assume that it's coming back the same path. The way to check it out is do a trace route from both directions. That's the way to fix that. Could I have a routing problem? Here I've got a device on the far left with address 192.168.5.4. So he's in the 192.168.5.0/24 network. And I want to get to a destination over in the far right, 10.10.10.10, 10.10.10.10.10, and I can't get there. What's going on? So I call the help desk, and we get one of the engineers, routing engineers involved, and he goes to the first router that the source is connected to, router 1, and he does a ping to 10.10.10.10, and it is successful. And he comes back to you and says, hey, not a network problem. Must be something with your PC. Is that really true? Well, let's find out. If that engineer does a second ping from router 1, but sources that ping from the interface on the left-hand side, the interface closest to the network 192.168.5, which is interface E0, that means he's going to use the source of that ping will be an address in the 192.168.5 network. So he sends that ping out to 10.10.10.10, and it fails. Aha! We in fact do have a routing problem. So if we go into the routing tables of router 1 and router 2 and router 3, are we missing something? Yes, we are. If we look at router 3, its routing table does not have the network 192.168.5 in it. So it has no way when destination 10.10.10.10 sends a response back to 192.168.5.4, it sends it to router 3 and says, can you send this response on? Router 3 says, I have no idea how to get that at network. I'm going to drop that packet. So this is an example of don't be fooled by pings. Do pings with different parameters, such as a different source interface, because by default, the source interface of a ping, particularly from any device, will be the interface that's closest to the destination. Always remember that. In this case, router 1's closest interface is E1, which it means that it would be an address in the 10.4.4 network, which all 3 routers have that in a routing table, that network. Okay. So that brings up the point about types of networks. You have connected, also called local networks, and then you have remote networks. And whether you're a connected, a local network, or a remote network depends on which router we're looking at. So in the case of network 192.168.5/24, it is a connected network as far as router 1's concerned. He is directly connected to that network. He did not have to learn about that network from anyone. It's directly connected to him. Now, from the perspective of router 2 and router 3, it's a remote network. Router 2 and router 3 don't just know a priori about the 192.168.5 network. They have to learn about it. And there are a couple of ways that can happen. You could go into router 2 and router 3 and put a static route in, or you can run a dynamic routing protocol like OSPF or EIGRP. But you have to tell those routers about that. So this problem that I just brought up an example of, we've got routing turned on. All the routers are run routing, but some reason, either we use static routing, we misconfigured something, or our dynamic routing protocol is not advertising a route that we need to, particularly the 192.168.5 network. So this happens a lot. Be aware of this. Now, run a dynamic routing protocol if you have any complexity or size in your network. And in my suggestion, I'd run OSPF. OSPF, it's a multi-vendor open standard. It's a great protocol. A little bit more complex or could be a little bit more complex than EIGRP, but it is a very good protocol. So are you running a dynamic routing protocol? Is it running correctly? You can do some commands to help that. Look at your config, do a show run. Do a show IP protocols command. You said you've configured OSPF, but let's look. Oh, let's say, yes, we're running OSPF, and I've announced routing for a couple of networks, and I'm talking to many sources that are talking OSPF to me. That all looks good, but ultimately I have to go to my routing table and do a show IP route, and there I do see that I've got some O routes. O routes are routes that I have actually learned via OSPF. Those are remote routes. So my OSPF seems to be working. The C routes are the connected routes, the routes that I instinctively know about. They're C as in connected. They're local. No one had to tell me about them. But if you're going to run a routing protocol, double check that it's actually working like you think it's working. And the ultimate litmus test is check the routing table. Okay. If you're running OSPF and you've got some problems, and again, I do recommend OSPF. I do recommend don't use RIP. I'm not a big RIP fan, especially if you've got any kind of loops or complexity in your network. Check your OSPF router neighborships. As a general rule, the routers that are talking OSPF to each other should have what's called a full relationship, and that's reflected in the output at the bottom of the screen. Now, if they don't have a full relationship, then that could be a problem. In the particular case of the top row on the show IP OSPF output, we have one that's in a two-way/druther relationship. I happen to know that this is okay. I won't go into details about why that is, but that is okay. But in most cases, particularly on point-to-point links, all those OSPF relationships should be full. No ifs, ands, or buts. Always check for MTU mismatches. That can be a problem with OSPF. Make sure that the neighbors agree that you're both in the same OSPF area. If one says I'm an OSPF 0 and one says I'm an OSPF 50, that's a problem. Make sure that the neighbors agree on the OSPF interface type, which is typically going to be broadcast or point-to-point, okay? And make sure that all of the IP addresses of all the interfaces that are running OSPF on your router are included in some sort of network statement, meaning we want the router to advertise these networks to other routers. So they learn about, hey, I can get you to networks 192, 168, 16, et cetera, et cetera. Okay. Just some odds and ends. Port channels. I like port channels. Also, the problems that you could have with port channels could also happen with equal cost multipath routing. That's when you have multiple links to get to between destinations A and B. I have multiple links to get there. Are all the links up? If one or more links is down, if things didn't go down cleanly, I might be losing packets. If I hash a source destination to a port that's got problems. I may have lack of entropy. Entropy is the idea that the more entropy you have, the more we're going to spread the packets across all the links at the same time, and that's good. But lack of entropy could mean that say you've got two 10 gig links, and 95% of the traffic is going over one link, and only 5% is going the other. So you're wasting your money. Maybe you need to adjust your hashing to get better entropy. Connecting third-party switches and routers, understand the nomenclature and defaults. You'll likely use LACP, Link Aggregation Control Protocol, on each end. Also, if you've got a networking problem, make sure there's no ACLs on any routers or switches that are blocking anything. Make sure that the firewall doesn't have an ACL blocking stuff that you really want to go through. If you're having performance with real-time applications such as voice and video, then check your QoS configuration. Or if you're not using QoS, maybe you need to start using QoS to make sure that those types of applications get priority behavior across the network. And then lastly, sometimes network problems can only be solved with more bandwidth. Certainly make sure your network is optimized before making any expenditures on bandwidth or new gear, but sometimes you just have to bite the bullet and get bigger pipes. No way around it. And then some final thoughts. Did you notice we didn't really talk about wireless much? And that's because aside from the unique RF aspects of wireless, understanding wireless networking troubleshooting, that foundational knowledge kind of emerges from its wired counterpart. They're very similar. And this was a basic session. Perhaps we can conduct a wireless troubleshooting session at a later time, but that would not lend itself to, in my opinion, to a basic session. All enterprise infrastructure and endpoint vendors offer a variety of tools to accomplish the diagnostic task we visited in this session, or at least they should. If you're going to put vendor X's gear in a large enterprise network, you better make sure they have the tools to help you troubleshoot it, because one day things will go in the dish. Document your network. If possible, use tools or dashboards that are self-documenting and always up to date. A good one that a lot of my customers use is they use Meraki, and the Meraki dashboard is very good at that. And also, learn how to use Wireshark or a similar tool. They are a great troubleshooting tool and a great learning tool. And lastly, good hunting. Wish you well in your endeavors. Any questions at this point? Hope this was of value to you. Let me see if we have any questions in the chat room. Let's see. Oh, yeah, someone made the comment And I really should have put it in there. Very good comment. Make sure you have current switch and router config backups, and make sure they are backed up regularly. That's a very good point, Adrian. Thank you. Very good. Okay. I don't see any other questions in the chat window. Does anyone have any questions you want to shout out? I hope this was helpful. And again, stay tuned for our update on IPv6. Tim Martin's going to give a great session. That is Thursday, March 14th at 9 a.m. And we will see you on the next Tech Talk, folks. You take it easy.
Thanks, Pat.
Thank y'all, folks.